In this video on Maclaurin series, we're going to be working towards developing a visual or graphical understanding of how a Maclaurin series actually converges towards a function. For that, we'll be defining Taylor polynomials or Maclaurin polynomials, and hopefully we'll be walking away from this video with a much better understanding of what the infinite sum that I've boxed in the upper right hand corner here, and whose first few terms I've written here, actually do or actually mean. One last thing I'll add is that by the end of this video, we'll also have some idea of what a Taylor series actually is and how it's connected to the Maclaurin series. All that being said, let's get started. At the top of the screen here, you can see that I've written the first three non-zero terms of the Maclaurin series for sine of x. You can also see in the lower right-hand corner of the screen that I've plotted the graph of y equals to sine of x on an xy grid. And so again, the idea here is for us to understand, or at least see, how this infinite sum will converge towards the curve that we see on the screen here. Alright, now the first thing we need to do here is define what a Taylor polynomial is. And when working with Maclaurin series, we'll also speak of a Maclaurin polynomial. So I'll just go ahead and write a quick title here, and I'll say Taylor polynomial. And as I just suggested, we'll often get away with also calling these Maclaurin polynomials. Maclaurin polynomial. In fact, a Maclaurin polynomial is nothing more than a Taylor polynomial that's been centered at 0. And don't worry, that will make far more sense by the end of this video. Alright, now if I use the Maclaurin series for sine of x here to define what a Taylor or Maclaurin polynomial actually is, I'll go ahead and copy this series, but I'll also include the 0 terms this series has. And that would look something like this. We'd have sine of x, which is equal to 0 plus x plus 0, that would be 0x squared, minus 1 over factorial 3x cubed, plus 0x to the power of 4, plus 1 over factorial 5 times x to the power of 5, and we could carry on forever that way. And now looking at this Maclaurin series, a Taylor or Maclaurin polynomial for this series is a partial sum of the terms that we see inside this series. And I'll just go ahead and define a few of the Taylor polynomials for this series, and I have no doubt you'll understand immediately. The first polynomial I'll write is p sub 0 of x. Well, that will be equal to the sum of the terms up to the 0th derivative of the function. And when I say 0th derivative, that would correspond to the very first term in the series. So p sub 0 of x would just be equal to the first term in the series we have here, so that would just be equal to 0. The next Taylor polynomial we'd have would be p sub 1 of x, and that's going to be equal to the sum of the terms up to the first derivative of our function, which would correspond to the second term in the series. So it's the sum of 0 and x, which would just be x. I carry on this way and I'll speak of the second order Taylor polynomial, which in this case would be p sub 2 of x, and that will be equal to the sum of the terms of the series up to the second derivative. So in this case that would be 0 plus x plus 0, so that would be equal to x again. And hopefully you get the idea. Carrying on this way, we could quickly go ahead and write that p sub 3 of x would be the third degree Taylor polynomial and would be equal to x minus 1 over factorial 3 times x cubed. The fourth degree Taylor polynomial would be equal to exactly the same thing, since the fourth derivative is equal to 0 when x equals to 0. And so we'd get x minus 1 over factorial 3 times x cubed again. And I'll stop at the next one. The fifth degree Taylor polynomial for this series would be equal to x minus 1 over factorial 3 times x cubed plus 1 over factorial 5 times x to the power of 5. And of course, we could carry on forever this way. Now, each and every single one of these is a Taylor or Maclaurin polynomial obtained from the infinite Maclaurin series we have here for sine of x. And hopefully it's clear now that we know what a Taylor or Maclaurin polynomial is. If we wanted to, we could go ahead and rewrite this infinite sum and state that f of x is equal to the limit, as n tends towards positive infinity, of p sub n of x. And I'll go ahead and box that result. There we go. In other words, as n tends towards positive infinity, the partial sum that we have from the terms of our series will turn into the infinite sum that we see here with the 3 dots at the end here. Okay, now that we have Taylor or Maclaurin polynomials out of the way, let's go ahead and see how well each of these approximates the curve y equals to sine of x on the sine graph that we have plotted on our screen here. Well, let's see, p sub 0 of x is just equal to 0, and so technically if I plotted that, that would just be the x-axis. So I'll be skipping this very first one here. But if I plot the first degree Taylor polynomial, so p sub 1 of x equals to x, it will look like this. And the key thing to notice here is that this blue line that we've just plotted, which remember is the first degree Taylor polynomial of our curve, has exactly the same gradient as our function f of x when x equals to 0. And as I've zoomed in on the screen here, we notice that for values of x close enough to 0, the blue line and the red curve, so the polynomial and y equals to sine of x, are basically indistinguishable. And what that tells us is that for small enough values of x, sine of x can comfortably be approximated by x, which if you study physics or engineering, you may well have already heard. That being said, I'll zoom back out and I'll carry on. And I'll quickly hide that first degree Taylor polynomial. Okay, skipping p sub 2 of x since it's equal to p sub 1 of x, if I now look at the third degree Taylor polynomial, and if I plot that on the graph we have here, it looks like this. Now in this case we have a cubic polynomial, and as we can see, and I'll zoom in a bit here, this cubic polynomial is definitely getting closer to the sine curve we started off with. Indeed, if we zoom in a little further here, we can see that the green curve and the red curve nearly overlap completely between x equals to -1 and x equals to 1. So this third degree Taylor polynomial allows us to approximate sine of x even further away from 0. And I'm sure you get the idea. The more terms we consider in our Taylor polynomial, the better the approximation gets for values of x further away from 0. And the words further away from 0 here are important, because indeed, if I were to zoom back in towards the origin, so close to 0, then this cubic polynomial approximates the sine curve very well, but just as well as the first degree Taylor polynomial did. Meaning for values of x close enough to 0, there's no real benefit in adding more terms. In fact, to convince you of that, let me plot y equals to x again. That was our first degree Taylor polynomial. Here we can see that the blue line overlaps the green curve, so the cubic, which in turn overlaps the sine curve. And for values of x between, say, -0.4 and 0.4, we can't really distinguish between the three, which suggests that the first degree and the third degree polynomial for x values between those two values are equally good approximations. That being said, I'll hide both the first degree and third degree Taylor polynomials. There we go. And I'll zoom back out a bit. I carry on, and I'll ignore the fourth degree Taylor polynomial since it's the same as the third, and I'll plot the fifth degree one. And so let's go ahead, if I click on that, there we go. And clearly we can see here that the fifth degree Taylor polynomial is a very good approximation to a sine curve for values of x which are even further away from 0. Indeed, if I were to zoom in a little bit here, we can see that this curve overlaps with the sine curve nearly all the way to the top around here. So the fifth degree Taylor polynomial is a very good approximation for x values which are even further away from 0. And of course we could carry on forever this way. And if I quickly zoom out, I'll show you a couple more. There we go. So that was the fifth degree Taylor polynomial, and if I hide that, here's the seventh, which is even better. And if I hide that and show you the ninth, it's even better. But now a very important thing to keep in mind here is that all of the Taylor polynomials we have here are good approximations to sine of x for values of x which are close to 0. And when we start trying to approximate sine of x for values of x which are further away from 0, then Taylor or Maclaurin polynomials turn into a lot of work. Indeed, looking at the screen here, as I'm sure you can appreciate, the Taylor polynomial that we plotted is the 9th degree Taylor polynomial. But even so, we've gone up to x to the power of 9, that Taylor or Maclaurin polynomial doesn't follow the sine curve for an entire period. And we could even go one step further. If we were to consider the 11th degree Taylor polynomial for sine of x, it looks something like this. And as an exercise for you to try, you could go ahead and plot the 13th, 15th, 17th, and 19th Taylor polynomials for the Maclaurin series for sine of x. And you'll see that it will take a lot of terms before you feel satisfied or confident that your Taylor polynomial is a good approximation to sine of x for x values further away from 0. And that's such an important fact. If nothing else, I hope that you will walk away from this video with the realization that when we approximate a function, like sine of x we have here, using a Maclaurin or Taylor polynomial, then it should only be used for values of x which are close to 0. As soon as we start looking into values of x which are further away from 0, then we need another solution to just adding more terms to the Maclaurin polynomial. It's simply not practical to keep on adding terms the way we did here. Luckily for us though, there's a nice and convenient way to deal with functions for values of x which are further away from the origin, and that is Taylor series. Now for all practical purposes, the Taylor series of a function works in exactly the same way as the Maclaurin series. In fact, a Maclaurin series is a Taylor series which is centered at 0. And you can see the formula for the Taylor series on the screen here, and hopefully you can appreciate that it's very similar to the formula we have for the Maclaurin series. The only difference being we're replacing the x we have here by x minus a, and instead of evaluating the derivative of f at 0, we'll be evaluating it at a each time. And so looking at the sine curve on the screen here, let me quickly show you what that would look like. Say we want to approximate our sine curve for values of x near 5 pi over 6. And 5 pi over 6 is roughly equal to 2.6, so that should be somewhere around here on our graph. And if I now add the third degree Taylor polynomial at x equals to 5 pi over 6, whose equation is on the screen now, the curve would look like this. And hopefully here you can appreciate that for values of x which are close to 5 pi over 6, the green curve we have here is very close, or dare I say, an excellent approximation to the sine curve in this region. And so to approximate sine of x near 5 pi over 6, we didn't have to go all the way to our 11th or 13th degree Maclaurin polynomial. Instead, all we did, or all we had to do, is go up to the third degree Taylor polynomial centered at 5 pi over 6 instead of 0. And if it helps, you can almost think of it as shifting our Maclaurin series along the x-axis by 5 pi over 6 units. And there we go. Hopefully you now have a good visual understanding of how a Maclaurin series converges towards a function as we add more and more terms in the series. And hopefully you're now comfortable with the fact that Maclaurin and Taylor polynomials are partial sums of the terms we have inside the Maclaurin or Taylor series. And last but not least, hopefully you're walking away from this video with a solid understanding of the fact that Maclaurin polynomials and the Maclaurin series should only be used when approximating functions for values of x which are close to 0. For any other value of x, we should be turning towards Taylor series and Taylor polynomials centered at that value of x. All that being said and done, that's it for this tutorial.